Okay, to conclude this week, we're going to come back again to optimization. And I'd like to introduce two key ideas. And mostly I'm going to sort of talk about these ideas and potentially demonstrate them in the context of actually code out of MATLAB. So we're not going to go into a lot of detail. More of the detail can be found in the notes. But I want to introduce you to two primary ideas. One is called linear programming. And the other is called genetic algorithms. Okay, so these are ideas that are important to us. Linear programming is quite old, sort of basically genetic algorithms. And you actually see why we have this name genetic in front of the algorithm. It's a very kind of a nice thing. But they're both optimization algorithms. Again, what they're trying to do is figure out ways that they can methodically go through and actually get you a solution to a given optimization problem. Okay, so the first thing is linear programming, as the name implies, can be applied to linear problems. Now we have other techniques can be applied, but what's beautiful about linear programming, it can handle constrained sometimes you can't spell very well, or I can't. Constrained optimization. In other words, the optimizations that we've done so far have been free of constraints. We haven't had to impose anything else. We just look at this objective function, and we're going to try to find where it's biggest. Here, it's not all about finding where it's biggest. It's about finding where it's biggest in feasible regimes. Okay? And the constraints can be imposed for various reasons. It could be coming out of your system. That you have to have, for instance, you might want to be optimizing some kind of stress-strain relationships, and you know material can only be strained at a certain amount. So if you find an optimal solution beyond these constraints, it's not even feasible because you'll have something break. The genetic algorithm is almost on the opposite side of this, which is the genetic algorithm. What it tries to do is it tries to solve very hard problems where you have no clear idea of any gradients in the problem that can be highly nonlinear, and that you want to try to figure out how can I actually even get a solution to this problem where it's a very large parameter space and none of the techniques that are aimed towards giving you a gradient even work. Okay? So this is for very complex problems. It pops up all over the place because a lot of problems nowadays when you try to optimize, if they're very complex with a lot of free parameters, none of the standard optimization routines are going to give you a result in any way. So the genetic algorithm, however, might be able to do something for you. Okay, so this is going to be the idea. The lecture itself today will be a little bit shorter, perhaps, but I just want to get to the computer and show you how to execute some of these on the computer, and we won't go into too much of the details about these, but the details, especially about the linear program, can be found in the notes, and it's related to the simplex method. All right, so let's talk about a linear program. A linear program is one that can be written in what's called the standard form. Or can be written in the standard form, which is the following. You want to minimize, again, it's an optimization problem, minimize some quantity, subject, here where the constraints come in, subject to something like this. So you have some quantity x. This is what you're trying to determine. And again, you see everything's linear here, right? This is a linear multiplication. So you have some quantities, and C tells you the weighting of the different quantity components. of the different variables. So you make up some objective function, and how you make that up is dependent upon c. C is just a vector of numbers. You know it. It's specified. X is unknown. Subject to, there's a bunch of constraints. AX equal to B constraints. So you can apply some constraints to the system. And let's say that, for instance, X is positive. So in this case, what we want to do is solve this thing. And there's a lot of ideas here that come out of this which are related to what we've done before, which is gradient descent. In these situations here, the way that you're going to solve this basically is developing the simplex method, which essentially is equivalent to going downhill. You're going to find a way to take a solution and roll it, always get to a better and better solution, iterate forward in time by essentially rolling a ball downhill. That's the way you can think about this. It's no different than anything else that we've done. If you look at the book, there's quite a bit more on the simplex method. And I don't want to kind of spend too much lecture time on the simplex method, but I'd encourage you to look it over because it's quite nice material. OK, so let's think about generalizing this a little bit, because I want to talk about this, but I want to start thinking about framing this in terms of MATLAB. So this is the standard way. And by the way, if what you're looking at isn't written in the standard form, a lot of times you can just transform it to the standard forms without much problem. But what I really want to consider is the MATLAB standard form that you could use. And the MATLAB standard form is a little bit more general. And this is what we want to do. So take this linear program, and you want to do the following. Minimize. OK, these are all vectors. Minimize this quantity here. This is your objective function. It's a linear objective function. That's important. Linear only. So one thing you have to know, if you have a linear function and you're trying to basically minimize it with respect to some constraints, you can always do it. Linear program is exactly what you want. The problem is very few things are linear, sometimes when you're trying to do the minimization problem itself. Subject to the following. Here's the standard form we want to consider for MATLAB. AX less than B. A hat x equal to B hat. So let's just say that these are all vectors so that I don't have to put the vector signs over the top. And also so I can denote A hat and B hat are two as a vector in another matrix. And x minus between x plus. OK, let's look at this form and talk a little bit about what this is doing. Here's my objective function, right? I have these variables x1, x2, all the way to x of n. And what I want to do is figure out how do I pick them such that this quantity here is minimal, right? So there's a weighting for each variable depending upon c. So c tells me how important x1, x2, and x3 are, and so forth, to this objective function. And I want to minimize this. But I can't just pick any values I want here. I also have the fact that a times x is less than b. So there's some constraints here that are inequality constraints. I also have equality constraints. Ax equals to b. And then I also have constraints on x. X has to be within some values. So this is a very general framework. You can solve almost any linear, you can solve all linear problems basically with this framework. So if you have a linear problem, linear programming is for you. It's going to find you the best solution. And by the way, how awesome is it in MATLAB to do this? There's the command, Linprog, for linear program. That's it. Let me tell you how you would put things in here. You see all these important quantities? The C vector, A, these are your constraints for inequality constraints, equality constraints, constraints on where things live. You would put them all in here. So in Linprogram, when you call this function, let me move over a little bit. You'd call the function, and you'd send in C, which tells you how you're weighting your objective function. You send in your matrix A and B, vector B. You send in these inequality constraints. You send in your equality constraints, A bar, B bar. You send in your x1, x2, which are, let's call these x1 and x2. This here's x1, that's x2. And x naught, okay? Which is your initial guess. Again, it's an iteration procedure. So it takes an initial guess and starts to try to roll downhill towards the best solution. That's what x naught is. By the way, why does it always give you this initial guess? Presumably, you are the expert in the loop. You kind of maybe know something about the problem. You have some idea of what kind of solutions might be reasonable. And based upon that, you might be able to give a good value for x naught. That's the assumption. For a very hard problem, maybe you don't know. Often is the case that if you don't have a good guess, in a lot of these, you don't have to even give it a guess. And you know what MATLAB does for a guess? It guesses 0. How about if I try 0, 0, 0, 0, 0? Well, okay, that makes that pretty nice. It doesn't necessarily make it minimum, because these can be negative. But if I pick all zeros here, but maybe it violates these constraints. And then it starts picking new values. It's an iteration procedure. But it has to start somewhere. And if you have a good place to start or something that's in the ballpark, you should use it. What does it spit out? Your solution, x. It's going to go through. It's going to find things. It can also spit out some other things. Fval and flag. The most important thing here is this flag. The flag that comes out tells you if you converged or not. Okay? So in other words, if you just say x is equal to, what happens if it got to a point and it didn't converge to anything? It might spit something out, but that's actually a solution that didn't work. So the flag always tells you if you converged or not. Any of the iteration procedures have a maximum number of iterations built in. So this thing here, even if it was going to converge, maybe it hit the maximum number of iterations. So for instance, if you have programs like gmres, bycg, stab, the maximum number of iterations is not very much. It's like 20. Well, if this is 20 iterations, what if it's getting towards a solution that stopped at 20? And that's it. So it gives you a solution, but it doesn't give you the converged solution. And all you care about is the converged solution, period. So you have to watch for that. You might want to watch for the flag. But this is it. That's the whole thing. X, fval, flag, linprog, done. Return. Cranks away, finds a solution, spits it out for you. This is amazing, really. This is at the power of your fingertips. Solve a very general problem. A few lines with one line of code. It's clean. So I wanted you to know about Linprog. And we're going to do an example here on MATLAB of executing Linprog. Okay? So Linprog is one. The other, so let's start with that. So let's do an example. So the example we're going to do in MATLAB is the following. Just show you how Linprog works. Example. Minimize the following. Minimize negative 2x1 minus x2. That's the function I want to minimize. In this case, you see what my vector c is, right? My vector c is -2, -1, essentially, subject to the following. x1 plus 8/3 x2 less than or equal to 4. x1 plus x2 less than or equal to 2. 2x1 less than or equal to 3. Minus x1 less than or equal to 0. Minus x2 less than or equal to 0. Notice what I've done is put it in the standard form of MATLAB. So in other words, what am I really saying here? Minus x1 is less than 0. What I'm really saying is x1's positive. Right? Here I'm really saying x1 is positive. So in other words, these are just forms of solutions, or this is just putting it in the standard form, because this is what's being required over here. MATLAB makes a decision. Here's the decision. AX, any kind of inequality constraint will be a less than constraint. Okay? Well, big deal. So you say, well, but my x1 is positive. Okay, well, then minus x1 is negative. Okay? So keep that in mind. You can always put it in this form. So here are the constraints. Less than, equal to, here. Now, in this problem here, I don't have any of this. We're going to leave that out for now. We're just going to say, look, suppose I just have these inequality constraints. I don't have any of these. We're just going to work with these two just for illustrative purposes. So this is what we have. We have these things here. Now let's go ahead and figure out what A, B, and C are. All right. Well, let's talk about the here. Remember, I want to write this as CT times X. Remember, X is X1, X2, these two quantities. Well, what's C then? Well, C, the vector C, is -2, -1. It's right from here. Those are the coefficients in front of those two terms. All right. Well, what about here? This is AX less than B. Well, the vector B is actually pretty easy to get, right? If you look at this here, this is less than B. Well, here's the right-hand side. It's less than, the first constraint is 4. It's less than 4. It's less than 2. It's less than 3. It's less than 0. It's less than 0. Right? So C is this, B is this, and what's A? Matrix A, well, what's the coefficients of x1, x2? 1, 8/3, 1, 1. Here it's 2, 0. Here it's -1, 0, 0, -1. A, B, C, and I ask the following question. Can I find, so here's some constraints, inequalities that must be satisfied in this optimization process. And what I want to do is find the best x1 and x2 that satisfies this. Okay? Everybody okay with that? So let's go program it. Because it should be pretty simple, right? There it is. All right. Linprog. Linprog. Fantastic. This is the kind of command, by the way. Let me just come out and say this to you. Linprog is the kind of command you want to have handy for your rest of your time at UW. This is an awesome command. I'm telling you right here. I'm looking at you in the camera. Keep this in mind. Linprog, you're going to use this later in life. Any kind of project you have and you're going to do some optimization, Linprog, keep it in mind. The whole point about this MATLAB that we're learning here is that it should be highly functional beyond this course. In other words, you should use this throughout the rest of your career here at the UW MATLAB. And then there's certain commands that are so awesome. They're the awesomest commands in MATLAB that you basically should be using, you'll be able to use in the future. And Linprog's one of these. This is quite amazing. So let's go ahead and program this up. So all I need to do in programming this is say, well, my C is -2, -1. My A matrix, what is it? Well, if you saw, there's 1 and then 8/3. That was the first row. Second row is 1, 1. Third row was 2, 0. Next row is -1, 0. Next row is 0, -1. done. And then b is equal to 4, 2, 3, 0, 0. And all you got to do now is say my solution, x is equal to Linprog. I put in my c, my a, my b. And that's all I got. I could put in a, I don't have, so let's look quick here on the board. We look back here on the board. Here's the Linprog setup. It's a Linprog, C, A, B, A bar, B bar, X1, X2, and a guess. I'm not going to give it a guess. I'm not going to give it constraints on the X values. I'm not going to give it equality constraints. All I'm giving is C, A, and B, so I can just cut off my bracket right there. That's it. Okay? So I'm just going to execute it and see what I get. And it's as simple as this. So let's go back over here. Let's see what solution comes out. So let's do a, okay, so now 1, 2, 3, go. It's running, done. Optimization terminated. My solution is 1.5.5. By the way, are those the right answers? Let's go to help Linprog. What I mean by that is, did it converge to a solution? Remember here I said, here's what you're going to do. Linprog, you give it f, a, and b. That's the simplest implementation. Returns the value of the objective function at x and f val, which is this guy here. In other words, it gives you back the objective function. If you, what f val is. That's, f val is the objective function, x is where it's located, and then you can do this, which gives you an exit flag. So let's do the following. Let's use that. X, f, which is my objective function, and flag. So now let's run it and see what happens. Here's my, so here are my values, 1.5, 0.5. My objective function, the minimum value is negative 3.5, and the flag is 1. What does the flag mean? Well, here's what the flag values are. If the flag is 1, the Linprog converged to a solution x. We got a flag 1, right? So that means that the solution we got was a converged solution. Here's where you got to be careful. If that flag would have come back 0, it would have means that the maximum number of iterations had been reached. And in that case, what we have to do is put some options in to make sure that we have more iterations. -2, no feasible solutions found. Number 3, unbounded solutions. Number 4, NNA values encountered. Number 5, both primal and dual problems are infeasible. Again, an infeasibility problem. -7, magnitude of search direction becomes too small. No further progress can be made. Problem is ill-posed or badly conditioned. So it's not like this thing works for everything. However, it works for a lot of stuff. And of course, you know, there are problems depending upon how you specify the constraints that could, of course, render this linear program not very effective. But for the most part, it's an amazingly powerful tool. OK. I think that's enough of Linprog. Like I said, though, this is a keeper. This is a routine you want to have available in your mind, at least if you have anything of this form. And again, it's very general. The biggest thing here is everything's linear. That's the constraint. But if you have problem that have any problem that is a linear optimization, dude, you should just use this. This is it. Linprog. Go. Okay? Look how much general this is. You know, equalities, inequalities. I can't, you know, I'm bounding where my solutions are. Minimized. Done. Awesome. Of course, if you want to write your own program, you could do so. I like this. This is 1, 2, 3, 4, 5, 6, 7 characters to type. That's pretty sweet. All right. One more quick comment about optimization routines. And I want to mention one, which is a package you can download from Stanford University, or actually, they put this out in open source. It's called CVX. it's at the following location, cvxr.com/cvx. What this is a convex optimization software that's downloadable for free. It's actually remarkably good. And it's free. And basically what it is, it's a downloadable software that basically interfaces with MATLAB. I'm not going to go into it except to tell you that this can handle an even broader set of problems than linear programming, the Linprog command. So CVX, if you need to do something a little more sophisticated, CVX is one potential way to do so. OK. So just keep that in mind. Convex optimization. Again, convex optimization, what does convex optimization mean? It means you have a hill to go down. It means you can give it a guess, and the way this convex optimization is set up is it's convex. It's a surface that you can always go downhill on. We are ultimately very limited about what we can do with optimization unless we have linear behavior, and so we can do Linprog, or we have some kind of convex function, which means we can always roll downhill somehow. Okay? Always keep that in mind about optimization. It's in the notes. You can download it. I actually use this quite a bit professionally. And I like the fact that it's free, and I like the fact that it interfaces with MATLAB very easily. There's even a help menu on it. It's also a really good program to have on your laptop for your time here at the UW. All right. Now we get to one last idea, which is quite important, I think. Which it comes down to this. If you think about everything we've been talking about linear programs. They work great. They're awesome. But you have to fit the form. You have to have a linear set of constraints, a linear objective function, a linear set of inequalities. Everything has to be linear. OK, good. And if you have that, you can work this thing out really nicely. Or you have to have some way to guarantee that you have convex optimization. In other words, that you can roll downhill on some function. In that case, you don't have to have the linearity constraint. But, gosh, you've got to have a hill to roll down. And if you want this thing to work, you got to have a hill to roll down. So convex optimization is awesome, provided your thing is convex. So it brings us to the last thing, which is the genetic algorithm. When all else fails, you don't have convexity. You don't have linearity. Then this might work. I like to say that it might work because you don't know if it's going to work, but you can always try it. And when you have a problem that none of these things hold, what you're hoping for is some method at least to try to figure out how to explore parameter space and make some kind of intelligent decisions about how to have the best solution. So the genetic algorithm was designed for this. So let's talk about how to do this. Again, it's doing the same problem we've always been working on. Minimize some function. But it can be a very high dimensional function, right? Let's not kid ourselves here. This looks really innocent, but this can be very complex, right? It can be a very complicated surface. And in some of what we've done with the gradient descent, and if this is a surface that you can roll downhill on, then you can use convex optimization. If it's linear, then you can do linear programming. But in general, this may just have some really complicated function. And x can be a lot of variables, so it can be very high dimensional. And then the question really comes to, well, what am I going to do? What are you going to do? All right. When in doubt, and you got nothing else, you can always guess, right? So why don't we do so? So here's how the genetic algorithm works. I don't know how to get values of x, so I'm going to guess some. So let's pick a bunch of guesses. So I'm going to guess a solution, xj. And what I'm going to do is guess, m guesses. In other words, I'm not going to just guess once. I'm going to guess m times. I'm going to say, well, what if we try x are these values, or those over there, or those over there, or those over there? I have no idea what's going to work. Let me just guess a bunch of them. Now, like I said, I've already set up the framing of the problem. You use this technique when other things fail. When you don't have convexity, when you don't have linearity, when you have a very high dimensional space and you have no, let's call it, informed algorithmic way to get to the solution, you just say guess. And in fact, maybe you generate these guesses from a random number generator. You say, oh, look, I have 100 variables. I don't know, let's make a random variable. Let's just fill it with random numbers. Throw it into here, see what I get. This is the basis of the genetic algorithm. Let me tell you why the name genetic is in there. So I'm going to take these m guesses. Okay? I've got, it could be a lot of them, right? So I try these guesses, I put it in there, see how they work. So after I guessed them all, I'm going to throw them in and I'm going to say, hey, were any of them any good? Out of all these m guesses, what I'm going to do is the following. I'm going to keep the following xj, and I'm going to throw away I'm going to keep p of them and throw away p to m of them. So suppose I take 100 guesses. I took 100 guesses. I looked at my objective function. And what I'm going to do I'm going to keep, let's say, the best 10 of them. And I'm going to throw away all other 90. Now, here's the idea behind the genetic algorithm, why it's called a genetic algorithm. What I did is I had this function, this objective function, that I had no idea about how to minimize. This is a high dimensional space. What I did is just randomly picked a bunch of guesses, and I just say, well, how did it do with my objective function? And everyone that comes back for every guess, I'm going to say, oh, that one did pretty well. That one's awful. Bad, bad. That one's pretty good. That one's bad. I'm going to evaluate them all. And what I'm going to do is keep the p best ones. Somehow, these guesses were better than all these. Okay? Now, it's a genetic algorithm because now what I'm going to do is from these p that I keep, oops, I'm going to discard, sorry. Sorry, here. From the ones that I keep, what I'm going to do is from these p that I keep that I thought were the best ones, let's suppose I had 100 guesses and I keep the best 10. So for the 10 that I keep, I'm going to take, for instance, one of them, and I'm going to create 9 mutations, or 10 mutations of this thing. Okay? Actually, sorry, 9 mutations. So I keep 10 of them. For each one, I make 9 mutations of it, let's say. And then take the next one, make 9 mutations of it. In other words, I take the parameter space I was in, and I perturb them all. So in other words, I take the x of j I get, and I just, perturb the take each value and kind of push them around a bit. So I have a new x of j up here. In fact, I have 9 new x of j based upon the fact that these 10 that I kept were the best. So I'm going to keep these 10 that were the best, and I'm going to wiggle them a little bit in parameter space. And I took 10 of them, and for each one of them, I created 9 mutants. And now I have 100 new guesses. I took the 10, I made, each one had 9 mutants, so I have a total of 100 again, and I put them back in here as my guesses. I run this, and I evaluate this objective function. And I do the same evaluation. OK, I took these 10 best, I created mutants, I ran the 100 again. What I'm going to do? Keep the 10 best again. These 10 best might be different than the 10 best previously. And then I'm going to mutate them, and mutate them, and mutate them. And what I'm going to do, this idea is it's like sort of like a genetic selectivity. Those that are fittest, in other words, those that give you the best results on this objective function, have the best possibility of surviving. In other words, you're going to evaluate them, and whoever gets the best score here is going to be retained here. And if you retain here, you keep iterating, iterating, iterating. With what hope? With the hope that, in fact, this thing might, in fact, converge to some really good solutions. That, in fact, you'll reach an optimal set of solutions x of j after a bunch of generations. So each time you go through, it's called a generation. That's the way the genetic algorithm works. You say, I take this thing, I prune off the weak, keep the strong I mutate, next generation goes through, I keep the strong, I prune the weak, I mutate the strong, next generation through. That's the idea of the genetic algorithm. Survival of the fittest, as it were, after many, many trials. So let's write a code to do this. And what we're going to do is the same problem we had done previously. So hopefully that has some kind of intuitive appeal to you, that in fact you kind of look at that and say, oh, that kind of makes sense. It should. Hopefully it does, right? That you're just going to, but notice how different it is than everything we've done so far. What's so different about this genetic algorithm is that everything we've done so far is sort of directed at, I'm going to write an algorithm that's going to go iterate right down to get me a solution. This one here is, I guess, I hope to get good solutions, and when I get them, I'm going to try to guess some more and guess some more with the hope that I'm going to converge. There are no guarantees that this thing converges at all. But in the fact, typically the kind of problems you try to apply this to, you don't have anything else, right? You're kind of out of luck. This is your last resort, as it were. So let's do the following. Let's take the data we had previously, and let's do a fit. We're going to do this. If you remember, we had used fmin search to fit this to some temperature data. And what I want to do is do the same thing again, but not use fmin search, but just to demonstrate this using the genetic algorithm. We're going to write our own genetic algorithm, but I will point out the fact that MATLAB has its own genetic algorithm built in, and we'll talk about that right at the end. OK, so let's go ahead and take some data and start evaluating this function. All right. OK. So where's my E to error? Oh. Okay, let's get rid of this. And unfortunately, I got to retype this the temperature data. OK, sorry about that. That's I wasn't thinking so far ahead. That's all right. We'll just type it back in. Here's my x. Here's my y. 75, 77, 76, 73, 69, 68, 59, 57, 55, 54, 52, 50, 50, 49, 49, 49, 50, 54, 56, 59, 63, 67, 72, 72. All right, hopefully that works. Uh-oh. vectors made of the same length. See, I missed something here. 75, 77, 76, 73, 69, 68. There's a 63 there. Okay, there's my data. And what I like to do is try to figure out if I can use a genetic algorithm to find A, B, and C for us. Okay, so some things I have to do. So there's my x and y data. And what I need to do is I need to plot, I need to decide a number of generations. Okay. We're going to do 200 generations. We'll do 50 trials. In other words, that's going to be the number of guesses we're going to give. For every time we do a trial, the 50, what we're going to do is keep 10 of those trials. So we're going to try 50, keep the best 10. Try new 50, keep the best 10. Try new 50, keep the best 10. Okay? And A is going to be, we guessed A to be something like 12, B to be like pi over 12, and C to be something like 60 or 62 last time. So let's start with that. But what we're going to do now is I have to have a bunch of guesses. So A will be 12 plus rand n by 1. So I'm just going to add a bunch of random values to this thing, plus rand n by 1 plus 60 plus rand n by 1. So these are my guesses. So what I'm trying to do here is within these codes, I'm saying n is 50, right? So what I need is 50 guesses. Well, here are my 50 guesses. I kind of have an idea that A, B, and C are roughly 12, pi over 12, or 60. So you see I'm solving this problem where I'm still doing an optimization. By the way, I could do this optimization just in standard ways, but here I'm going to go ahead and do it with this way, so which is here are 50 guesses for A, B, and C. So those are my initial 50 guesses. So now we have a loop for j equals 1, 2, the number of generations m. Call this j gen. Those are the number of generations, the generation loop. So what I want to do is evaluate the objective function for all these guesses for j equals 1 to n. So n is 50, right? And I want to just say, look, I'm trying to minimize the error. This is my objective function right here. It's Cj minus y. There. See this? This is my least square error. And what I'm going to do is I'm going to come in here and I'm going to evaluate that error for all 50 guesses that I have. And what I want to do is keep the best 10. Okay? I want to keep the very best 10 of these. And the way you do this is to say, I'm going to sort these based upon, let's do this, ES, EJ is equal to sort E. This is going to sort from small to large. And what I want is small. Okay? If you want to check out what sort does, you say help sort. Okay? So what it gives you is sort. It gives you here two numbers, the index where the things are stored and the values themselves. Okay, so that's what we're getting here with ES and EJ. So ES here is the value of the function sorted from smallest to largest, and EJ tells me which vector component it's in. So in other words, suppose that my best solution is 5 and it's in the third component, then I get 5 and third. So E, remember, is a vector of length 50, and I want to make sure I pull out the right vector components. So to keep the best 10 components, here they are. AK1 is, sorry. I want to go ahead and pull out first 10 of these. Okay? So EJ 1 through 10, or 1 through 10, gives me what the index numbers are, and this is going to give me then, I'm going to pull these out into this A. Okay. So that is going to be the new A values right here. See, I'm making a new vector of A values, K1, which the first thing I do is pull in my best 10 that I have for A. I got to pull in my best 10 I have for B. I got to pull in my best 10 I have for C. Okay? Now, I have to create, for each one of these best guesses, I want to create 10 new mutations, right? I want 50 new solutions, right? So I already have 10 solutions. Here they are. I got to generate 40 more. What I want to do is take these 10 best and mutate them. Okay? So let's make a mutation. AK2 is equal to AK1, right? So it's the same thing plus some randomness. And I'm going to divide this by a number of generations. Okay, that's just to scale it. And then I have BK2 is equal to what were the B values before that were good, and now mutate them. Create some new ones off the mutated things. And finally, CK2 is equal to CK1 plus rand and N2, 1. So what I just did there is I took my 10 best that I had, I added mutations, and I created a new set of A's, a new set of B's, a new set of C's. And so I can just copy and paste this. And we'll call this AK3, and these AK4, AK5. And there we go. I have now a bunch of new generations. So my new A value, A is equal to, I want 50 A values, right? So A is going to be AK1, AK2, AK3, AK4, and AK5. And I'm going to get something similar for B, so I'm going to just copy and paste this. Again, more efficient ways to program it, but this is just really to illustrate for you how this might go. B, come on, B, 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 C. See, now I have 50 new values, and I have the 10 that I kept, plus each 10 that I kept, I mutated. The 10 that I kept, I mutated 4 times. So now I have 50 guesses, 50 new guesses, and I just go through this loop. And that's it. So what we want to do is, after we're all done, it's going to give me some values for A, B, and C. And the question is, are those the best values for A, B, and C? Okay? So what I want to do is go ahead and find those out, and I'm going to plot them. Where's my plot here? All right, so let me plot all those results here. And actually, let's do the following. For each generation, what I want to do is I'm going to do the following. You see this error here? What I'm getting out of here is the error vector. And what I'm going to do is plot E. So what I do is when I plot E, and I'm going to pause for 2 seconds. So you're going to see the error of all 50 iterations, all 50 trials, and then you're going to see, watch this thing converge. Ready? Go. Let's see if this works. There's the error. There's the error, next iteration. Now look at this. This is 3rd generation, 4th generation, 5th generation. Look at this error. It's huge. So it's almost 6,000, 5,000. We're just watching this thing go down. Watch this thing. Maybe it's taking too long. 2 seconds is too long. Let's kind of speed that up a little bit. Okay. Let's go and watch this thing for half a second and go. There we go. Look at that. That thing is iterating away. Look at this. I got a lot of good solutions down here. I still have some really bad ones. But watch this thing sort of converge. If you remember, this thing was up at 6,000 or 7,000. Now it's coming down. It's coming down. So not bad. See, now it's kind of sort of in the thousands, 1200s. I keep trying to get better and better solutions. And it's going to go, it's going to go. Look at this. Now I'm down here to my error being, some of my best solutions are down here, and their error is sort of in the 50s or 60s. And it's sort of a nice convergence. Look at this thing converge down. So what I'm doing essentially is pruning away bad guesses in favor of good guesses. And even though I keep perturbing it and keep watching this thing perturb, look at this thing sort of converge. Now look at this. This thing's down here now to 300. Is this sort of whatever the error means. But you know, now we're down here to 300, 200. And remember, we started off with this thing being around 7,000. And we're just guessing. We're just guessing, taking our best guesses, perturbing our best guesses, guessing again, and you're just seeing this thing starting to converge down. This is kind of remarkable. And after a lot of generations, then it actually sort of converges quite nicely. In fact, what we're going to look at here in a moment is the final values here. So you can see the best are still in the top 10 or best are still here. Look at this. This is now under 200. And we started with the error of like 8,000 or 9,000. And so now it's still looking around. You know, what you're seeing here is when you perturb this thing, it looks for new solutions, right? So it's always trying to go out there and say, okay, I'm going to go try for new solutions. It tries for new solutions. And if it can find some, it'll give them to you. So, but you look here, and I've got some really good solutions down here in this bottom left corner. Some things that really worked well. In fact, if I plot that, let's in fact plot what the solution looks like. So I could just go ahead and plot here. Let's plot this down here, plot x, y. And then I also want to plot on here, I want to take these values of A, B, and C, my best ones. So I can do this by doing this, whatever I ended up with. And I'm going to take my best value, my top one. And in doing so, I can say, okay, now make a function. I'm going to make the function f, which is equal to ak1 times cosine bk1 times x plus ck1. That's going to be my best guess. Then I can plot x versus f. So let me just copy and paste this into the command window so that you can see this. There. Check it out. That is the result from the genetic algorithm, which is almost the same. It's probably exactly the same as you're going to get, like at least within 10 to the minus 6, as you get with fmin search. Completely different way of solving this. Final comments then. So you see, this genetic algorithm, it's a guessing, but it's kind of a smart way to guess. The genetic algorithm tries to find something, it looks for something for you, and you tell it how to go look about it. It prunes off the best solutions, goes find things. And we just wrote a little code there that actually solved the curve fit problem for us just fine. Quite a bit slower than fmin search. But remember, the genetic algorithm is not trying to compete with fmin search. It's trying to solve problems that fmin search has no hope of solving, or that Linprog has no hope of solving. Okay, so just keep that in mind. The genetic algorithm in MATLAB. Let me just show you the basic structure of it. Genetic algorithm, GA. That's it. And here's how it works. You call some right-hand side function. You call a function called fit.m. And in this function, it's just like fmin search. You give it the thing you're trying to optimize. You give it the function. This function is the thing I'm trying to minimize. Remember, in fmin search, that's all you give it. You say, I want to minimize like this error. Here's the error. Minimize it for me. And what you give it, N, A, B, A bar, B bar, X1, X2, go minimize what's in here. Use that many generations. Here are your inequality constraints. Here are your equality constraints. Here is your constraints between x1 and x2. Let's not worry about these. That's it. Actually, amazingly enough, notice that these are linear constraints, linear inequality constraints, linear constraints. These are linear brackets. It's not bigger, it's bigger than this, it's less than this. You can impose nonlinear constraints and options. That's the generic form. Kind of amazing. So you go and this thing will just try to, it just does like what we did. It's going to just guess a bunch of solutions. Let's guess a bunch of solutions, see which ones work best. From the ones that work best, we'll keep those, mutate them, throw them in, which ones work best, mutate the best of those, do it again and again and again, and you saw that this thing actually converged to the solution, even though I just sort of randomly guessed. This is what this does. So that's enough for optimization. You should keep these optimization routines in mind between Linprog, the genetic algorithm, fmin search. You have amazing tools to do things for you. And you shouldn't forget that you have access to these. And you should keep in mind when you should use one versus the other. And that's it for the optimization.